All right, so we're going to look at question 5 from section 1.5. So, big idea here is that we're going to interpret a derivative. So, done a lot of exercises so far where we find derivatives in these functions that don't really have a context, but now we're going to look at functions that have a context and talk about what the derivative really means in those terms. So, first we're being asked to find a derivative of this function f, specifically at the value of 10. And we're going to use a central difference. So let me write down the more common definition of the limit definition of derivative, which is not a central difference, but I will show you how we modify one to get the other. So the limit of as h goes to 0 of f of x plus h minus f of x over h. So, and again, this comes back from a slope calculation. So what is our change in y values divided by some change in h values? And the thing that makes it a derivative is the fact that we're trying to make h as small as possible. See what happens as h approaches 0. So this is the more standard, the one that's definitely more common to you, the limit definition of a derivative. The central difference is instead of having some base value of x and using h to kind of deviate from there, we are going to deviate on both sides from the base point, in this case 10. So here's essentially what we're going to do. I am going to, and we're given this h value of 0.01. So I want to evaluate the function at 10 plus 0.01. I want to evaluate the function at 10 minus 0.01. And when I divide that by, for now, I'll talk about the difference in these points. So these are the difference in y values. What's the difference in x values? The difference in x values, 10 plus 0.01 minus 10 minus 0.01. So what's going to happen in the denominator there? The 10s are going to cancel. I'm going to have 0.01 minus negative 0.01. So that's positive 0.02. So basically, since our h is 0.01, but since both of our points are deviating from 10 by that much, that's when we get double that difference as our change in x. So for the rest of this, let's evaluate this function here at both of these values. So what is f of 10.01? Give me a second here. So 10.01 times 0.05 negative, if I raise e to that, times 110 plus 75. So the value I get there is 141.69. And then if I do the same thing with 9.99, so 9.99 times 0.05 negative, raise e to that number, times 110 plus 75. What do I get? I get 141.75. So very small difference here. Minus 141. So final result I get is this, negative 3.087. So that's the number I get for the derivative using this central difference. So that's just the numerical value. Let's talk now about what that is. So in part B, again, remind you of the numerical 3.087, negative 3.087, and we're asked to do some interpretation now. What are the units on the value of this? So we just found a rate that unites f and t. So it's the rate of change of whatever f is as a function of the rate of change of whatever T is. So let's think about what those things are. So F, capital F, represents in degrees Fahrenheit the temperature of this cup of coffee. So because of that, the units on this better involve capital F, and something that the very first thing we talked about this semester was covariation, and you can't really talk about derivatives without thinking about how two quantities vary together. And in this case, those two quantities are the one we just identified, the temperature of this coffee, measured in degrees Fahrenheit. What's the other part of this rate? It's going to be whatever E is expressed in, which in this case is minutes. So the units we have here are degrees Fahrenheit per minute. So now those are the units. Second part of this question, what is the practical meaning of this value? So what does this value mean? So we can actually learn a lot about that from the units it's expressed in. So basically what this is saying is, for every, unit change in time, in this case, that unit is minutes, we're looking at the derivative. So what we really estimated is the instantaneous rate of change. So at this instant in time, at t equals 10 minutes, the temperature of our cup of coffee is changing by 3.087 degrees Fahrenheit per minute. But we can even be a little more specific and do better than that. We have a negative number. So what does that mean about the cup of coffee? Well, it means it's actually cooling down. So at time equals 10 minutes, this cup of coffee is cooling down at the instantaneous rate of 3.087 degrees Fahrenheit per minute. All right, moving on to part C. Which do we expect to be greater, f prime of 10 or f prime of 20? So a lot of ways we can kind of go at this. The first way I'm going to choose to do so is think about what's happening here, or what this function represents. This function represents a cup of coffee. And if we think about the temperatures that, let's remind ourselves where these numbers came from. This right here was f of 10.01. So the temperature slightly after 10 minutes. And this right here was the temperature at 9.99. So the temperature is slightly before that 10-minute mark. Does it make sense that the earlier one is higher? Well, hopefully I can use that information to convince you that this cup of coffee is cooling down. What happens to a cup of coffee as it cools down? Does it just cool down forever until it freezes? No, it's going to cool down until it, gets close to whatever the temperature is around it. So that's one way that I could say that I believe that f prime of 10 is going to be greater. Think about when you have something really hot. Maybe you're a coffee drinker and this is something that makes sense to you in that context, or maybe you just pulled something out of the microwave. When is it cooling down more rapidly? Or in the terms of covariation, when is the temperature changing more significantly with respect to equal changes in the time? Is that when you first stop heating it, or is that much, much later? And hopefully that makes a little more intuitive sense that, for earlier times, the cooling rate is going to be more rapid. It's going to be cooling down at a faster rate. So that's one way I could say that I think f prime of 10 is going to be greater. For another, and there's probably so many ways to interpret this, and I by no means think I'm going to come up with all of them. But another way is to look at this function. I am not going to graph this, but you're more than welcome to if you want. If we look at this exponential function, we have e raised to the negative 0.05 t. If I think about what that's going to look like if t gets really, really big, as t gets really, really big, this exponent is going to get, very large in magnitude, but it's also going to be negative, which means I'm going to end up this e to that number is going to get really, really small. Going to kind of go towards 0. So that leads me to believe that as T gets very, very big, my temperature is going to get closer and closer and closer to 75. And hopefully that kind of is consistent with the way you think about something cooling down. At some point, it gets very near the temperature of the environment outside of it, and basically the cooling gets a lot less significant. So part D, write a sentence that describes the behavior of the function f prime of t. So on the interval from 0 to 30. And it's also asking how that graph will look, so maybe we should try to draw a graph. So let's just break this up into chunks here. So 10 minutes, 20 minutes, and 30 minutes. And we actually have some data. So what did we say our rate was at 10 minutes? We said it was negative 3 and change. So if this is my time axis, and I want to graph not f, but f prime. So I think this is a point I have. So -1, -2, and -3. So based on some of the other things I said, I think that it's also fair to say that if I choose times less than 10, I believe my cooling rate is going to be even more rapid, because the difference between the temperature of the coffee and the temperature of the surrounding room is going to be much more different. I believe that rate is going to be more significant at the beginning, and I believe that rate is going to diminish as time goes on, because we'll be getting closer and closer to the temperature of the coffee. One thing I want to point out about my graph here is that these are all these derivatives are negative. So does that make sense? What does it mean that all these derivatives are going to be negative? Well, since we're talking about f prime, which is the rate at which the temperature of this coffee cup changes with respect to time, it's always going to be cooling down. Coffee cup came out, we know at 10 minutes it was about 141 degrees. It's always going to be cooling down. So because it's always going to be cooling, that means f prime will always be negative. So hopefully it makes sense that my graph here only contains negative values. As for why it's diminishing, so we have a derivative here that is always negative, but as time goes on, it looks like this derivative gets less and less negative. It gets closer and closer to 0. And hopefully that makes sense based on some of the other things we've said about this coffee cup cooling down. As time goes on, it's going to have less cooling to do. It's going to be cooling down at a less rapid rate. So we were only asked to graph this thing to time equals 30, but if we were to look far in the future, maybe I'm putting this break here because I want to say, let's say time is 1,000,000 minutes. If we go out that far, we're going to get to the point where the cooling is so minuscule, but still negative. It's still going to be, technically speaking, maybe it's not perceptible. Maybe it's not like maybe you won't be able to feel the differences, but it's still going to be hotter than the room temperature. All right. So hopefully this makes sense. Please let me know if you have any questions.